In 2025, inside a clean room sealed from the outside world, IBM quietly revealed something that might change computing forever. A new class of quantum machines, faster, cleaner, and more connected, and fabricated using the same industrial scale technology that makes the world's most advanced classical chips. They claim quantum advantage by 2026 and fault tolerant quantum computing by 2029. That sounds impossible until you look at what they actually built. At the annual Quantum Developer Conference, Jay Gambetta walked on stage with a message that didn't sound like a keynote. It sounded like a declaration. IBM is the only company positioned to rapidly invent and scale quantum software, hardware, fabrication, and error correction. He wasn't joking. IBM bought receipts, big ones. They unveiled IBM's Quantum Nighthawk, their most advanced processor ever, and introduced an entire fault-tolerant architecture called Loon. Then came the boldest part. IBM believes the first verified quantum advantage will be confirmed by the community and not just themselves by the end of 2026. Not hype, not simulation, but verified. This is Nighthawk, 120 qubits arranged in a square lattice, but the real magic is in the connectivity. Nighthawk links qubits using 218 next-generation tunable couplers. That's a 20% increase from IBM's last major chip, Heron. Why does this matter? A qubit alone is like a singer warming up a backstage, but computation begins only when qubits interact, and that's when they're entangled. Tunable couplers are like tiny switches that control these interactions. More couplers equal to more communication, more entanglement, more computational complexity, and fewer errors. IBM claims this lets users run circuits 30% more complex than on Heron, while keeping error rates low. And the gate count? Nighthawk supports 5,000 2-qubit gates. By 2026, 7,500 gates. By 2027, 10,000 gates. By 2028, 15,000 gates via long-range couplers. Long-range couplers, by the way, are exactly what they sound like. Quantum long-distance phone lines that let faraway qubits talk directly. This opens the door to 1,000-plus qubit machines with usable connectivity. Quantum advantage isn't quantum beats classical in everything. It's one provable case where quantum wins. Just one. To keep this transparent, IBM partnered with Algorithmic IQ, the Flatiron Institute, and Blue Qubit to launch an open quantum advantage tracker. Right now, the tracker monitors 3 major challenge categories: observable estimation, variational problems, problems with efficient classical verification. These aren't toy problems. Algorithmic IQ's model already pushed today's classical methods to their limit. Sabrina Maniscalco put it bluntly. These models challenge all state-of-the-art classical approaches. IBM expects the first real verified win by late 2026. A global countdown has officially begun. Hardware is only half the story. To control qubits, noisy, fragile, unpredictable qubits, you need software built in like a scientific scalpel. Enter Qiskit, IBM's quantum software stack. The new updates bring dynamic circuits that are nothing but quantum if-else logic, which are essential for algorithms like error correction. The new update also brings 24% accuracy boost at 100 plus qubits, thanks to the improved circuit control. HPC accelerated error mitigation that's 100x cheaper, and new C++ interface and a C API, so that the HPC teams can integrate quantum into the existing workflows. Error mitigation is like taking multiple blurry pictures and averaging them to get a sharper one. It doesn't fix the errors, but it reduces their impact. Fault tolerance, however, eliminates them, and that leads us to Loon. If Nighthawk is the sprinter, Loon is the marathon runner. Loon includes every component needed for fault-tolerant quantum computing: multi-layer routing, low-loss connections, long-range on-chip couplers, fast reset of qubits, architecture designed specifically for QLDPC error correction. But here's the part that stunned the community. IBM proved that classical hardware can decode QLDPC errors in under 480 nanoseconds, a full year ahead of schedule. QLDPC codes are like quantum seatbelts. They protect qubits by storing information redundantly. But the trick is, you must detect and correct errors faster than they occur. 480 nanoseconds is blisteringly fast. It means IBM's classical hardware and quantum hardware can now talk at the speed necessary for real-time correction. This is one of the missing pieces of the fault-tolerant puzzle, and IBM just solved it. This next part is why IBM might actually hit 2029, and why many competitors won't. IBM moved quantum chip production to a 300mm semiconductor fabrication facility. Not a small research lab, a real industrial-grade automated fab. This changes everything. Development cycles cut in half, complexity increased 10x, parallel design exploration. This is the same facility behind IBM's 2nm classical chip breakthroughs, the Albany Nanotech Complex. It runs 24/7. It uses state-of-the-art EUV-level equipment, and it's deeply integrated with IBM's Yorktown Heights Research Center. Christy Tyberg, who helped lead this transition, said, "If we hadn't moved to Albany using 300mm technology, we couldn't have achieved our roadmap." This isn't just scaling, it's industrializing quantum computing, just like classical chips industrialized after the 1970s. Nighthawk and Loon aren't just machines. They're the result of hundreds of engineers, physicists, and fabricators working like a single organism. Many came from classical semiconductor backgrounds. People like Hemant Jagannathan, who worked on 2nm chip technologies and multi-layer packaging. When he joined Quantum Project, he realized quantum wasn't like classical. Everything had to be built from scratch. Writing layers, couplers, materials, architectures, none of the playbooks existed. The team wrote them from zero under intense time pressure. Their culture became one of the rapid iteration. Design, fabricate, test, fix, repeat. 7 days a week, sometimes around the clock. This is how Nighthawk and Loon left the fab on a schedule. The roadmap doesn't stop at Nighthawk and Loon. Next comes Kookaburra, Cockatoo, Starling, Limujii, each with more qubits, better connectivity, lower error rates, and deeper integration with classical supercomputers. This is a long march, and IBM is treating it like a military campaign. Every technological revolution has a moment when dream becomes engineering. Transistors in the 50s, microprocessors in the 70s, deep learning in the 2010s. And now in the mid-2020s, we may be watching the dawn of fault-tolerant quantum computing. Maybe IBM hits 2029, maybe they slip, maybe they surprise the world again. But one thing is clear. The quantum frontier is no longer theoretical. It's being built, layer by layer, coupler by coupler, qubit by qubit, in a 300mm clean room in Albany. The future isn't coming, it's already running on a quantum chip.